In this lesson, we're going to be taking a look at what are known as the special triangles, and then what those special triangles can tell us. The reason why we have special triangles when we're talking about trigonometry is that there are certain angles that come up so frequently, and they're just so fundamentally useful in trigonometry that we should know the exact values that go along with the trigonometric ratios, sine, cosine, and tangent for those angles. The angles, as I've listed here, 30, 45, 60, and 90, and then it's also multiples of those angles as we go on to larger angles as well. But for this lesson, we're just going to focus on 30, 45, 60, and 90. There's an obvious angle that's not included here, which is 0 degrees, and we will be talking about that. But of course, that's an angle of 0 is a very special case, and I will save that for later. Really, when people talk about these special angles, they're mostly concerned about 30, 45, and 60 degrees. 90 degrees comes up because we're generally talking about right angle triangles as well. So let's go ahead and talk about how we can make use of and come up with the relationships related to those angles. First of all, I'm going to start off with a square with a side length of 1. And the first thing I'm going to do with that square is I'm actually going to cut it in half. So I'm going to take that square and I'm going to make a cut corner to corner on that square. Now, if I do this, obviously this is still a side length of 1. But now that I've drawn in this diagonal, and since it's a square, let me introduce the idea of that right angle. That's where 90 degrees starts to make its presence known. So if I cut this square in half, as I've done here, I end up with this. And what we have is half of the square. So now we're dealing with just the triangle. Now with this triangle, at one point in time, we had right angles in these other corners as well, when it was a square. So if I have cut this square exactly in half, then the angle that I have in those other corners is now going to be 45 degrees in each corner. So you can see that we've created this triangle that is symmetric. It has one of those special angles, which is 45 degrees. And we have this unknown side. And I'm going to label that h for the hypotenuse. The Pythagorean relationship tells me that the hypotenuse squared is going to be equal to the sum of the squares of the other sides. But that's just going to be 1 squared plus 1 squared. So I end up with h squared is equal to 1 plus 1. H squared is equal to 2, or h is equal to the square root of 2. And we don't worry about the plus or minus here because h is a dimension on a geometric figure, and lengths and dimensions must be greater than 0. So we only consider the positive one here. At this point, we can now relate the special triangle. So let me replace that h with the value of the square root of 2. And now we can come up with the trigonometric relationships for this. And so those are going to be, whenever I have the sine of 45 degrees, if you ever have this situation, I want you to be thinking about recognizing the angle 45 degrees. That's one of the special angles from a special triangle. Sine is opposite over hypotenuse. That's going to be the same as 1 over the square root of 2. Typically, we rationalize denominators, which is the process of not having any square roots in the denominator. Now, anybody who's familiar with special triangles, 1 over root 2 is something they're going to be completely familiar with. So if you write it in that form, or if you see it in that form, people are going to recognize it. But in terms of a final answer, there is a certain tradition or convention around this process of rationalizing. There'll be times when you see it, and there'll be times when you don't. The way I rationalize this is I want to get rid of the radical in the denominator. I multiply top and bottom by root 2, which means I'm just multiplying by 1. I'm not actually changing anything, but I'm just changing its form, and I end up with sine of 45 degrees is equal to root 2 over 2. Or as I say, you will also see it as 1 over root 2. The cosine of 45 degrees, cosine of 45 degrees is adjacent over hypotenuse, which it turns out is also 1 over root 2, which of course we can rationalize to be root 2 over 2. And the tangent of 45 degrees is from 45 degrees opposite over adjacent. Well, that's just 1 over 1, which simplifies to 1. In the case of the 45-degree special triangle, notice that it doesn't matter which of these two angles I use. Of course, I'm going to come up with the same set of relationships. As far as naming, this triangle is, you could refer to this as the 45-degree, 45-degree, 90-degree triangle, and it is sometimes referred to that way. Much more commonly, I feel that it's referred to as the 1, 1, root 2 triangle. That's just based on my own experience. I feel like the 1, 1, root 2, the important part here is remembering the side lengths that go along with it. Remember, the hypotenuse is the longer side, and so square root of 2 is about 1.4, so that's bigger than the 1 and the other 1. And in the note, I have just included a nice computer graphics version. So you can even see here more formally, that's probably because of something our textbook says. I also quite often refer to it as the 1, 1, root 2 triangle. And I do think that repeating this is going to help you remember what those side lengths are. Let's go through a similar exercise, except for now we're going to start off with an equilateral triangle where all the sides start off with a length of 2. So all 3 of these sides, that's what an equilateral triangle means. If all the sides are equal, that means that all the angles must be equal as well. So that means we have 60 degrees, 60 degrees, and 60 degrees. What I'm going to do with this triangle, similar to what I did before, I'm going to cut it in half, but where I cut it in half is going to be a little different. Now I'm going to go from the vertex of the triangle to the middle of the opposite side. And that's going to have some interesting effects. For example, that means that this side length is going to be half of 2. So now I have a side length of 1. And this angle is going to be half of 60 degrees, which means it's going to be 30 degrees. Now this diagram's already getting a little cluttered. So how about we switch to a fresh diagram? And now I can label that side 1. Now I can label that angle 30. I already had an angle of 60 here. I already had a side length of 2 here. And there was a right angle in this corner. Notice that the side length that's missing this time is here. It's vertical. So I'm going to call this y because that is not my hypotenuse. Horizontally, I think of it as an x direction, vertically as a y direction. So I'm going to use a vertical variable for this. I'm going to call it y. The relationship from Pythagorean theorem tells me that 2 squared must be equal to the sum of the squares. So 2 squared is the hypotenuse squared, is equal to the sum of the squares of the other side. So that's 1 squared plus y squared. And so we end up with 4 equals 1 plus y squared, which of course that means that y squared itself is equal to 3, or y is the square root of 3. And because in this case y is a dimension, y has to be greater than 0. So this side is the square root of 3. And as I was talking about naming, I'll do it in a reverse order here. This is referred to as the 30, 60, 90 triangle, or it is referred to as the 1, 2, root 3 triangle. And I tend to call it the 1, 2, root 3 triangle because I do think that helps students remember what the side lengths are. Just as we did before, let's take a look at our trig ratios. Now this triangle includes the 30 degrees and 60 degrees, which means I have a little bit more to do here. Let's start with the smaller angle. The sine of 30 degrees is opposite, which is 1, over hypotenuse, which is 2. So the sine of 30 degrees is a half. That's already in a reduced fraction form. We don't have to do anything more about that. The cosine of 30 degrees is going to be starting with the 30-degree angle as my angle of interest, adjacent, which is root 3, over hypotenuse. And that's over 2. So root 3 over 2. I don't have to make any more adjustments. There's no rationalization to occur here. The tan of 30 degrees is equal to opposite over adjacent. This is 1 over the square root of 3, which can be rationalized. Multiply top and bottom by root 3. That's going to remove the square root of 3 from the denominator, and we end up with root 3 over 3. Doing the same process for 60 degrees as our angle of interest. The sine of 60 degrees. Sine of 60 is root 3 over 2. Not root 30, pardon me. Root 3 over 2. The cosine of 60 degrees is equal to adjacent over hypotenuse. That's 1 over 2. And the tangent of 60 degrees is equal to opposite over adjacent. That's root 3 over 1, which, of course, just simplifies as root 3. We don't normally write a denominator of 1. The other thing that I'd like to bring to your attention is the fact that the cosine of 30 degrees is exactly the same as the sine of 60 degrees, and that the sine of 30 degrees is exactly the same as the cosine of 60 degrees. And the relationship there has to do with the angles. The reason why that relationship is there has to do with the fact that 30 degrees and 60 degrees, those are known as supplementary angles because they add up to 90 degrees. 30 degrees and 60 degrees add up to 90 degrees. And so that is why that relationship is there. Hold on a second. Let me just, if I'm going to do color coding here, I'll do it this way. So the fact that that exists has to do with this relationship between sine and cosine and the angle 90 degrees, which of course is very important in these triangles that we're looking at. And I have the graphical summary, a nicely printed graphical summary of what I just went through there. So whenever you see those angles, 30, 45, 60 degrees, or whenever you see these distinctive values in the ratios, square root of 3 is a giveaway from the previous one, the 45-degree triangle, square root of 2. Whenever you see those, you should be wondering, at least, you should be considering whether or not you can apply that to a special triangle. And then I've got an exercise here about evaluate using exact values and express your answer in a reduced form. Now, in some cases, that instruction is not necessary, but in other cases, we will need to do a little bit more work. I'm just going to, over on the side here, just remind us of both of our special triangles. So 45 degrees, 1, root 2. And my 30 degree, 60 degree has 1, 2, root 3, and that has a right angle. So the sine of 45 degrees, so you don't have to keep these things just in, you don't have to do this stuff by trying to picture them mentally. you can write things down. I actually encourage you to do this. The best way to get these committed to memory is on every fresh page where you are doing some exercises dealing with trigonometry. Just sketch out each of the special triangles in the corner, and believe me, after you've done that several times, it will start to feel quite natural to you. Always sketch them out in the same way. Whenever I draw the 30, 60, 90 triangle, I always draw it with the same orientation. I've been doing this for decades, literally. I always have the 30-degree angle at the top. I always have the 60-degree angle in the bottom left. And I always have the right angle in the bottom right. I always, always, always do it that way. So the sine of 45 degrees, the sine of 45 degrees is opposite over hypotenuse. So you could write this using the triangle, which is 1 over root 2, and then rationalize that to become root 2 over 2. Or you might remember that it is root 2 over 2 and go straight to that answer. One of the examples, or at least one of the examples that we're going to work on here, is going to illustrate, I hope, why it's useful to write it in this rationalized form. The cosine squared of 60 degrees. The cosine squared of 60 degrees is just another way of writing the cosine of 60 degrees all squared. So it means figure out the cosine of 60 first and then square it. Well, the cosine of 60 degrees is adjacent over hypotenuse. That's 1/2. And then we square that, and our final answer is 1/4. Nothing more for us to do with that. How about this next example? Cosine of 45 degrees plus sine of 30 degrees. The cosine of 45 degrees is adjacent over hypotenuse. That's 1 over root 2. Plus the sine of 30 degrees. The sine of 30 degrees is opposite over hypotenuse. The sine of 30 degrees is 1/2. Now, between root 2 and 2, coming up with a common denominator and then combining this fraction is actually non-trivial. That's a very awkward kind of denominator to come up with. And this is, from the research that I've been able to do, this is one of the better arguments for why we rationalize. If I put the cosine of 45 degrees into its rationalized form, first of all, now the denominators are at least going to be integer values. So if you always rationalize away any radicals out of your denominator, then any denominators you have in fractions are going to be are going to be integers, and it's going to make it that much easier to combine these. Now, in this case, it's actually very simple because they both have a common denominator of 2, and we could write this as root 2 plus 1, but it seems like the convention for writing radicals like this, when it is a mixed radical where you have some terms that are integers or numbers and some terms that are in radicals, it seems like the convention is that you write the radicals afterwards. So this would typically be written as 1 plus root 2 over 2. And let's look at our final example. 2 tan of 60 degrees minus 3 tan of 30 degrees. I've introduced these integer multiples at the beginning of each of the trigonometric terms. So that means I take 2 multiplied by the tan of 60. Well, the tan of 60 is root 3 over 1, which we typically would just write as square root of 3, minus 3 times the tan of 30, which the tan of 30 is 1 over root 3. That's opposite over adjacent. So we could write that as 1 over root 3. And you could do what I'm about to do here, or you could recognize, oh, 1 over root 3, I could write that as a rationalized form right away. You might recognize that as root 3 over 3. Either of those is fine, whether you do that little piece in your head or whether you take the time to take 1 over root 3 and then maybe in some rough, then you rationalize that to on its own. And then here we end up with, of course, well, the answer root 3 over 3. I've already told you what that is. So 2 times the square root of 3, we normally just write that as 2 root 3. And then here we have the 3 divides out with the 3. And what that's going to give us, those both become 1. So this actually becomes minus the square root of 3. And minus the square root of 3 here, that's really like saying 2 square roots of 3 minus 1 square root of 3. Now, if I had 2x minus 1x, you would know immediately what to do with that. 2 of these things minus 1 of these things. So it is exactly the same here. 2 root 3 minus 1 root 3 is 1 root 3, or in other words, we would just write that as the square root of 3. And that is it for this discussion of the special triangles and how you make use of them.